On this episode of Science with a Twist, new research makes oxygen tell a whole new story about how the moon was formed. I'm your host, Marshall Bradshaw, and welcome to Science with a Twist. Many theories have tried to explain how the Earth's moon came to be, but they each have their own flaws. Let's start off with the capture theory, which states that the moon used to have an independent orbit before it got caught up in the Earth's gravity. This theory fails to explain why the moon and the Earth have a shared chemistry. Both bodies have the same collection of oxygen isotopes. This doesn't seem to be true for any other celestial body in our solar system, so how could the moon and the Earth match so perfectly? The next and most popular theory is called the giant impact hypothesis. According to it, a Mars-sized body called Theia collided with the Earth at just the right speed and angle for the moon to be formed by the debris. But again, how did the two end up with the same makeup of oxygen isotopes? An older theory proposed by George Darwin, son of the famous Charles Darwin, is fission theory. It imagines a young Earth that spun so fast the moon was slowly torn out of it, leaving the Pacific Ocean behind. This would explain the isotopes, but does not fit with our current understanding of the moon, the Earth, or the Pacific Ocean for that matter. Finally, accretion theory says that the moon formed just like the Earth, out of the dust that became our solar system, and it did so more or less right where it is now. This means that the Earth and the moon would have been a binary system from the very start. This theory might explain the shared isotopes, but it doesn't explain the moon's particular orbit. The giant impact hypothesis, however, would explain the moon's orbit, at least according to a 2012 study published in Science by Matja Chuk and Sarah Stewart. Here's the twist. What we thought we knew about the shared makeup of oxygen isotopes is wrong. To recap, we thought the moon and the Earth had a similar oxygen isotope makeup. In 2001, Science published a study by Whiteshirt et al. Supporting this. It found no distinction between the ratio of different oxygen isotopes on Earth or in lunar soil brought back by the Apollo program. But since then, more advanced methods have been devised. According to a new study by Hurwitz et al. Published in the 6th June 2014 issue of Science, there are some differences. Hurwitz and his team used new methods on fresher lunar samples, and they were able to detect a slightly but distinctly higher composition of oxygen isotopes in the moon. This bolsters the giant impact hypothesis. It's possible the impact balanced out the isotopes, making their differences harder to see, but now we can tell that these two bodies do have distinct histories. It goes to show the importance of revisiting old studies and challenging the proven. That's all for Science with a Twist. Thanks for watching.